So in this video, we will go over the integral test to determine if the series converges or diverges. So yeah, now let's just continue on with the different types of tests. Suppose f is continuous positive decreasing function on intervals bracket 1 to infinity and a of n equals f of n, then the series of the summation of a of n is convergent if and only if the improper integral from 1 to infinity f of x d of x is convergent. So you would only use this test when the function is easy to integrate or when you have an ln. So that's when I would only use the integral test. It also must be continuous, positive, and decreasing. If it doesn't satisfy all three conditions, then you cannot use the integral test. Okay, so yeah, so it has to satisfy three conditions. And I would use this if it's easy to integrate. So example one says, use the integral test to find the convergence / divergence. So we have the integration from n equals 1 to infinity of 1 over n squared. So what I would do is maybe rewrite this. I think this could be a p-series, right? You can rewrite this as the integration. Right? This is the same thing as this. So it's a p-series. Our p is 2, which is greater than 1. And you can use the p-series test or you can use the integral test. Okay. So yes, let's do the integral test. So we can rewrite this as the limit, or if you want to take the integral test, you would rewrite this as the integration from 1 to infinity of 1 over n squared dn. And then the limit, you can limit as a approaches infinity of the integral 1 of a of 1 over n squared dn. And then you apply your fundamental theorem. So what is the integration of 1 over n squared? Well, that's the same thing as n to the negative 2, and then that would be the limit as a approaches infinity of negative 1 over n. And then you apply your fundamental theorem. Upper minus lower, so that would be so if you apply the upper, it would be negative 1 over a minus 1 over 1 and then the limit as a approaches infinity of negative 1 over a. Two negatives becomes positive, so that's plus 1. And then you can put your plug in your a for infinity, so it's going to be negative 1 over infinity plus 1. And then what is uh, 1 over a very large number is 0, and then you have this negative, which is really 0 plus 1. So 0, negative 0 plus 1 is now positive 1. Okay, so it's 1, and because it's a real number, it's going to converge, right? It's not infinity or negative infinity. Okay, so I did that using the limit comparison test. You could have also used the p-series test. Let's move on to example 2. So example 2, use the integral test to find the convergence / divergence. Okay. So first we got to satisfy, can we use the integral test, right? Can we? So it has to satisfy 3 conditions. It has to be continuous, positive, and decreasing. So this square root graph is not continuous. So this 1 over square root of n minus 3 is not continuous, so we cannot use any integral test. Okay. If we use the comparison test, so we might have to use the comparison test. So if you recall in the comparison test, you got to choose the biggest term on the top over the biggest term on the bottom. So step 1, choose biggest term. Over biggest term on the bottom. So that's going to be 1 over square root. So the biggest term on the top is 1, and then the biggest term on the bottom is square root of n, which is going to be 1 over, and then square root of n is the same thing as n to the 1/2, right? And how can you rewrite this as 1 over n to the 1/2? So now you can use the p-series. So if you recall in the p-series, our p is going to be 1/2, which is less than equal to 1. So then step 2 is you're going to take the limit as n approaches infinity of original over choice, which is equal to the tangible number. Okay. Now, you could use the integral test if n is equal to 4. So wait, hold on. So this, so the problem to this one, to the answer to this problem, it diverges because um, we did the comparison test and then we use the p-series test, and our p is 1/2, which is less than equal to 1. So that means it diverges, right? We could not use the integral test because it is not continuous. Because it goes from infinity, right? But let's say let's pretend it wasn't infinity. Let's say our boundary is from 1 to 4, right? So if or not because like if I mean not one, because like if you look here, if you plug in 1 - 3, that's like not even real. But if you made n to 4, I believe it could be continuous, right? So at it if let's look at this problem if n equals 4. Then we could use the integral test, right? So let's pretend n is equal 4. Then you may use the integral test. Okay. So yeah, if we started at 4 to infinity, it would work. So then you could use the integral test. So it would be from 4 to infinity of 1 over square root of n - 3 of dn. And then it would be the limit as a approaches infinity from 4 to a. And then you can use u substitution. So your u substitution would be u equals n - 3, and then my du would be dn. So it's going to be the limit as a approaches infinity 1 over square root of u du. Uh, what can we do? I guess we can say u equals n - 3. And then we said that our u is n - 3. And then, yeah, so it would be, so our n is 4. So it's going to be 4 - 3, just 1. So u equals a - 3. So we can rewrite this integral from 1 to a - 3. Of 1 over square root of u du. And then let's just continue. One over square root of u is the same thing as u to the -1/2 du. So that's going to be the limit as a approaches infinity. And then the integration of u to the -1 is 2 square root of u. Then you may apply your lower and upper. So the limit as a approaches infinity to square root of a minus 2 minus 2 square root of 1. Whoops, why is this a 2? It should be 3. And then minus 2 square root of 1. So what would that be? So the limit as a approaches infinity of 2 square root of a minus 3. And then square root of 1 is 1 minus 2. That's minus 2. So that's going to be infinity minus 2, which is infinity, just diverge. Let's move on. Example 3. Use the integral test to find the convergence / divergence. So can we use the integral test? So is it positive and continuous? I think it is, right? So can we use the integral test? So you could ask yourself, is it positive and continuous? I believe so, right? Because if you plug in 2, it's not going to be like an infinity number, right? So I think it is positive and continuous. So we can use the integral test. So it would be from the integrals of 2 to infinity of 1 over n ln of n of dn. So that's going to be the limit as a approaches infinity of the integrals to a over n ln 2 of dn. If we do use substitution, if u equals ln of 2, du is going to be 1/2, 1n dn. And then dn equals n du. Okay, so the limit as a approaches infinity from the integral 1 over nu times n du. And if u equals ln of u would be ln of a. Okay, so the limit as a approaches infinity of your new integral, if this would be 1 over u du, and that's going to be the limit as a approaches infinity from the integrals ln of 2 and ln of u is 1 over u du. Say which is infinity of ln of absolute value of u of 2 ln of a. That's going to be the limit as a approaches infinity ln of absolute value of ln of a minus ln of ln of 2. So that's going to be the ln of ln of infinity minus ln of ln of 2. And that's going to be what? Ln of absolute value of ln of infinity is a very large number, or infinity, minus ln of absolute value of ln of 2. Well, ln of 2 is a number. Ln of a number is a number, so it's going to be a small number or a real number. So a very large number minus a very small number is going to be infinity. Right? If you look at it graphically, the graph ln of 2 would look something like this. Right? As a goes to positive infinity, the y slowly starts to increase. So it diverges because it's infinity, right? So it's infinity and it diverges. Okay. So that wraps it up for integral test. I mean, yeah, in the integral test. I'll stop here.